Hello, and welcome to today's webinar, Precision, Control, and Repeatability, Harnessing the Power of UV Curing in Medical Manufacturing. I'm Amanda Hosey, your moderator for this 30-minute program, which focuses on the transformative capabilities of modern UV curing systems. Our speakers today are Divyanshu Divi Gupta and Roy Kaiser of Excelitas Technologies. Divi is a product manager who oversees the Omnicure spot curing solutions at Excelitas Technologies. He holds a master's degree in applied materials engineering and has a wealth of experience in UV curing, materials engineering, and process optimization across various applications. Roy is a senior global application manager at Excelitas with more than 29 years of extensive engineering and integration experience. He's the author of numerous resources on UV curing solutions and holds 12 patents for power and light source applications. If you have questions for our speakers, please send them through the Ask a Question box and we'll address as many as possible at the end of the program. Now, on to the presentation. Welcome, Roy and Divi.
Thank you. I'll start off with a brief introduction of Excelitas, what we do, and the UV curing product line. We'll move on to, just for beginners, what UV curing is, what are the advantages of UV curing, what are the key process variables that must be considered when designing or trying to improve your UV curing process, how you can optimize your process even more, and finally we'll have some time for a brief Q&A session. So starting off, Excelitas Technologies, we are a company which specializes in photonics solutions. We've got a deep portfolio of innovative photonic technologies, light sources, including lasers. And within that division, we have Omnicure, which specializes in UV curing light sources, LED-based and lamp-based. Then we have some other product lines for optics and optomechanics, sensors and detectors, and some power supplies as well. We are really a global company. We've got design and manufacturing locations in Americas, Europe, and Asia. On this slide here, you can see a brief breakdown of our UV curing product portfolio. So we have spot curing solutions as well as larger area curing solutions. Within spot curing, we have traditional mercury lamp-based sources, and then some LED spot-based sources, which we call our LX series as well. And then over on the right, you see our larger LED-based area curing light sources. So we have a lot of experience, over 30 years experience manufacturing, designing UV light sources, and our products are used in a wide variety of industries, especially medical device manufacturing and assembly. The S series spot curing system is a leader in spot curing applications for medical device assembly. Moving on, we'll just do a brief of what is UV curing. A lot of you may already be aware. So UV curing, short for ultraviolet curing, employs UV light to cure adhesives, coatings, or inks. UV forms a very narrow band of the electromagnetic radiation spectrum, as you see right here. It's slightly higher energy than visible light, and then within UV, you can have multiple, there are multiple bands called UVA, UVB, C, and V, based on their wavelength range. UV curing is very rapid and precise. Used in applications where you need a really strong and sterile bond based on whatever adhesive you're using. For that reason, it's very particularly critical in healthcare industry applications. Curing is basically a chemical reaction which is kicked off by UV light in this case. The UV light interacts with the adhesive. There are some photoinitiators within the adhesive which respond to UV light and start the polymerization reaction. Polymerization causes the adhesive or the material to solidify, or as we call it, cure, and that basically results in sticking of two things together. Just something to keep in mind, photoinitiators are chemicals which are sensitive to UV light. We can have different types of photoinitiators within an adhesive, ionic and free radical. And based on whatever your application is, it becomes important which one you're choosing. We'll come back to photo initiators in a little bit when we talk about types of UV sources and which type of source to use for what adhesive. Some typical applications for UV spot curing. The biggest one we have is catheter bonding. On the right here, you'll see some images of a setup that uses one of our S-series lamp-based system being used to assemble a catheter tip. You'll see four light sources on the right around it. Another application is optical fiber bonding, wound dressings and bandages, IV sets assembly, uh, dental device manufacturing, surgical instruments, and hearing aid assembly. As you'll see, there's wide applications right across medical device assembly. A lot of these applications involve uh, devices that would go inside the human body. So uh, anywhere where you need a biocompatible uh, bond or you need high precision bonding, such as optical fibers. These are now really small components and require very high precision to be assembled correctly. Um, some of the key benefits of UV curing. The first off, it's cure on demand. Some of the traditional bonding mechanisms or adhesives, such as the ones that are heat cured or air dried, they can take a lot of time to fully cure. It can be hours or even days, whereas with UV, it's instantaneous, from few seconds to 2 to 3 minutes. This can speed up your assembly process by a lot. The Your assembly would be ready for the next step within seconds. And of course, that will lead to reduced cycle times, higher production, and ease of automation. UV curing also offers a lot of control over the curing process. You can change your speed, your depth, and degree of cure by varying the process parameters, the exposure duration, intensity, and so on. And it is very energy efficient as well. Compared to traditional bonding methods, thermal, waterborne, or solvent-based adhesives, you uh, don't consume a lot of energy. You don't need large drying ovens or uh, any of those capital equipments to extract VOCs that are given out by some of these water solvent based adhesives. Uh, so you save a lot on your manufacturing floor as well. You use less space uh, versus traditional assembly methods. The adhesives available, they come in a variety of options with tunable viscosities, and that gives you a lot of flexibility on the dispensing methods as well. And finally, it's very environmental friendly. There are no volatile organic compound emissions that can greatly benefit in uh, meeting stricter and stricter regulatory requirements. Now, let's look at some of the key process variables that you must keep in mind when designing your UV curing process. The first and foremost is the UV curing power and the wavelength sensitivity of the adhesive and the substrate. We'll talk about all of these in a bit more detail. I'm just listing down the key process variables right now. Second up is your curing setup design, the substrate itself, the environment, and finally how you control the process, how you monitor your process, measure it, and control it to make sure it's repeatable. Now, starting off with UV curing power, this by far is the most critical when designing your curing process. This is basically how much UV dose your material formulation needs to fully cure and uh, give you the final properties that you want. We define UV curing power in three steps. First is intensity. So this is basically energy that is being delivered per unit area. Uh, As you would expect, if higher intensity would accelerate the cure, the adhesive would solidify faster, but at the same time, it must be balanced. It is possible to cure an adhesive too quickly and over cure it as well. In those cases, you wouldn't get uh, the desired physical properties that you want. If you cure too quickly, you could have stress concentrations, the adhesive could crack. There could also be discoloration, which might be undesirable in certain applications. Next is the dosage. So this is basically the product of intensity and time. Your light source would deliver some intensity, but the substrate has to be exposed to that intensity for a certain duration of time for a consistent cure. And thirdly, it's the wavelength. So each light source would have a different spectral output. It might be monochromatic, such as an LED source, where it only delivers one particular wavelength, or like a lamp-based source that can be broadband, where there are multiple wavelengths within that spectrum. Um, and typically, a really good place to start uh, or to get information about what your UV adhesive wants is to refer the technical data sheet. Manufacturers of adhesives, coatings, they do a lot of research and provide data on what the wavelength sensitivity is, what kind of light source is required for that adhesive, and what is the typical dosage and intensity requirements. That usually gives you a really good place to start while designing your process. And then, of course, you need to do some testing at different intensities, different dosages to fine tune it further for your specific requirement. Um, Factors affecting your UV curing power, the light source itself. Lamps are typically very high powered, whereas LEDs are lower powered, but as I said, they are uh, specific to one wavelength. Lamp to substrate distance and exposure time. We'll talk about lamp to substrate distance in coming slides. And finally, if you optimize these variables, you can improve your curing process a lot. You can have proper curing depth and quality, reduced energy consumption, and minimize risk of over curing and under curing as well. So how do you control and measure your lamp intensity? Um, as we like to say for QA purposes, no measurement is no control. Both lamp and LED based UV sources, they degrade over time. Some degrade faster than the others. Typically, lamp based sources decay a lot faster than LEDs. Uh, so if you, let's say, set your process today, uh, it's very likely after 100 hours of use, the lamp output or the LED output would be a lot lower, and you wouldn't be getting the same consistent results as you were when you designed your process. So it's really essential to measure and control the LED output. One of the easiest way to do it would be with a radiometer. Radiometers can be used to measure the output and calibrate the light source. Now, the radiometer itself must also be optimized for the light source you're using. There are radiometers which are tuned for a broadband output versus radiometers which are tuned for LED or monochromatic light sources. Um, and these can be integrated right with your system, so you can have a periodic calibration uh, schedule for your curing setup. Another way to add an additional layer of protection is closed loop feedback. Now, this is something that is exclusive to Excelitas Omnicure systems. What this technology does is we build in a photodiode within our systems, which continuously takes a sample of the light output. So you see the lamp in green here, and on the bottom there's a mirror which is taking a sample of that light and delivering it to a photodiode. Based on this sample of light, the system can automatically adjust for any degradation of the lamp over its service life. Uh, as it detects lower and lower output, it can adjust the iris position, which is really controlling the output lamp intensity to kind of compensate for that. And with that, what you get is a much more consistent output for your process. Uh, Another method that has been used in some high-speed manufacturing applications is dynamic lamp intensity control. So, an example would be a continuous manufacturing line which can have varying speeds. So, if your manufacturing line is varying in speed, there might be some components which spend more time illuminated by the UV, which can then result into an overcure. What you can do is take an input from your line speed and feed it into the UV curing system itself, and which can then vary the lamp intensity based on that input. So if your production line slows down, the intensity from the lamp decreases as well in the same proportion. So you can get a consistent cure even when your production speed is varying. Again, this is something that's built into some of the OmniCure UV curing systems where you can provide an analog signal through the PLC input, which can act as a lamp intensity control. Um, then setting your process window. Typically, you would like to have some buffer, plus minus 20% buffer in your process window. This can not only allow you to get good quality output, but also will help you get more life out of your uh, light sources. So typically, as I mentioned, any light source would degrade with use. If you use your light source always at 100% intensity, you'll typically see a very low service life. So it's usually recommended to use the light source at not more than 80% of its maximum value, so that as it degrades, you have a 20% window to accommodate for that degradation and get higher service life out of your light source. Moving on, lamp to substrate distance. So, as you would expect, as you move further away from your light source, the intensity or the energy per unit area that your adhesive is receiving decreases, and it decreases very drastically, uh, and it's proportional to the square of the distance. So if you move twice as away from your uh, light source, so let's say you move from 2 millimeters to 4 millimeters, your intensity would actually drop by a factor of 4. On the top right, you see a typical beam or intensity versus distance profile for one of our spot curing systems. And as you'll see, as you move further away from the light source, the intensity decreases by a lot. At 8 millimeters, it's at 25 watt per centimeter square, but just at and it can drop to as low as 10 when you move further away. There are certain optics or optical lenses that you can use to focus the light to a specific working distance. So uh, that can give you a higher flexibility with your process. So as you see in the graph, even though 5 millimeter is closer to the lens, the intensity at 5 millimeter is lower. As you move away from 5 to 8 millimeter, the intensity increases. So that is achieved with a specific lens which is designed to focus the light at a 8 millimeter working distance and hence provide the optimal performance at a slightly higher distance from the source. So it's very important to choose the type of lens, the type of optics correctly for your substrate and for your curing setup. Uh, Here I have some additional examples which can further help illustrate uh, uh, a light source without a lens versus a light source with the optical focusing lens. And as you'll see with a lens, the degradation or the reduction in irradiance is a lot lower, which will help your process give that extra or have that extra flexibility and tolerance to variations. Next up, which wavelength to choose? As we discussed in the beginning, wavelength is really important, and it's determined by what kind of material formulation you're using and or what kind of adhesive you're using. The photo initiators in a adhesive, they are sensitive to a particular wavelength, and they must have that particular wavelength to start the curing process. And that would determine what kind of a light source you can use, whether it's a lamp based or an LED based. Um, as you'll see in the spectral output graph that just showed up, the output of a lamp versus LED is very different. You'll see the blue line, which is a typical mercury-based lamp output. It has a lot of wavelengths and it has a lot of intensity within those wavelengths as well. Whereas the LED-based sources, they are lower output and they are limited to a particular wavelength. So the choice of the light source would heavily depend on what kind of photo initiators are present in your material. They can also impact your cure quality at the end. Uh, Typically, higher wavelengths have more penetration as well. So, for example, if you're just using a 365 nanometer LED, you may see a really good cure on the surface, but then you might have uncured material further deep down. Uh, so again, depending on your adhesive, depending on the cure depth that you want, you might want to use a combination of light sources. So say 4 or 5 nanometer with the 365 nanometer, 4 or 5 nanometer being higher wavelength, it has a much higher penetration, and both of these combined can give you a good surface as well as a deeper cure uh, on your bond. Moving up. We already talked about adhesives. What some people miss a lot of times is the substrate as well. Your substrate can also impact the performance of your light source and your curing process. Uh, in a lot of cases, the substrate would compete for the UV light being illuminated on the bond. Even the substrate would have a certain absorption curve. So for example, your adhesive needs 365 nanometer light, but your substrate also has a very high absorption at 365 nanometer and low transmission consequently for that. In this case, again, first off, the adhesive won't receive as much light, and secondly, a lot of the UV light would be absorbed by the substrate, which would then be converted into heat by the substrate. So you're not only wasting energy, but you're also introducing a lot of heat into your process, which can again negatively impact your cure quality and finally physical properties of your uh, bond. Curing environment, it's also something that can usually get overlooked. The moisture content, and specifically the oxygen concentration in your environment can greatly impact your surface finish. A lot of time, customers come to us and they say the surface isn't curing well, and the surface is tacky or sticky, and these are the cases where we would typically recommend to do a nitrogen purge, which can help remove oxygen from the surface, and it greatly helps improve the surface cure quality. Um, Another important or another way to improve the quality of your cure can be step curing. With step curing is basically a curing technique that involves curing the material in multiple stages. at different curing parameters. So you can have an exposure 1, which is a lower intensity for a shorter time, and then an exposure 2, which is, let's say, higher intensity for a longer time interval. This can be very useful if you're doing thick bond lines or if your assemblies are very sensitive to positioning, uh, as is, as is, as is in the case of optical lenses or microelectronics assembly. What this can help you do is reduce localized strain. So you do a first cure, which is at lower intensity. It helps stack your components, and meanwhile it helps relieve strain. Then you do your second cure, and by the time the components are already fixed in place, there is not a lot of strain in the adhesive, which can finally prevent cracking, prevent movement of the components during assembly. And again, this is something that can be programmed right on some of the OmniCure UV curing systems. And finally, with Industry 4.0, the newer UV curing systems also have a lot of features built in for real-time monitoring that can really help you go to the next level in terms of process control. Uh, you can track each and every exposure. You can track intensity, duration, and if it was a successful exposure or not. And all of this can be remotely uh, monitored and controlled over the internet or basically any communication method that you might want. Um, that is all we had for the presentation right now. Now I will stop for some questions.
All right, great. Thanks so much, Debbie, for that presentation. And yes, just a reminder to the audience, you can still submit questions for Debbie and Roy through the Ask a Question box on your screen. Now we have some questions that have already come in. So first up, what should be taken into account when transitioning from a lamp source to LED for UV curing?
So I can take that question. Several factors were discussed in the presentation, but from a high-level standpoint, you have to take a look at the adhesive sensitivity to wavelength. Are there multiple photoinitiators in the adhesive or the coating or whatever it is you're trying to cure? That will help guide you towards either lamp or LED. If the photoinitiator is sensitive to a more narrow band of UV energy, then we can focus on LED and then pick the appropriate wavelength. Other things that you have to take into account are, what are you curing through? So if you are curing through a substrate, we have to take a look at the optical transmission of the substrate to make sure that the wavelength of energy that we're choosing can pass through. So those are the main high-level points to consider when looking at LED or arc lamp and picking your source and adhesive.
Great, thanks so much for that, Roy. Next question, someone asks, what is overcure and how can you overpolymerize?
So I can take that question as well. Overcuring happens when you are delivering too much energy into the material to be cured. What will happen is eventually you'll have a heat buildup within the material, which can cause discoloring. This will lead to a runaway effect where the discoloration will absorb additional amounts of UV energy, create additional heat, and eventually your bond could outright break down, or your material will become brittle and its longevity would be greatly reduced. So basically, too much energy equals overcure, and your process window should be designed to compensate for that.
All right, great. Thanks, Roy. Another question says, referring to slide 12, which I'll go back to now, what about with the aging from the sensor?
So I can take that question as well. The sensor within our S2000, our S-series units, is a photodiode, but it is calibrated with our, what we call R2000 radiometer. So the mistraceability of calibration lies within the R2000 radiometer. It is required to calibrate yearly in order to maintain its accuracy. Once we calibrate our S2000 systems with the R2000, because again it is now mistraceable, it transfers energy readings to the S2000, thereby passing on its traceability to NIST. And therefore, the sensor inside the S2000 has a new correlation factor of output intensity to, photocurrent is really what we're looking at inside our system. So long story short, we are periodically calibrating the internal sensor with the R2000 if you do own an R2000.
All right. Thank you so much, Roy. And I know we're over time, but let's take one more quick question before we go. Someone asks, will stepped curing reduce shrinkage of the UV material?
I can take that question as well. So yes, that is one of the benefits of employing a step cure process. What happens is with a very small ingress of UV energy, it causes like a pre-cure, or you could almost call it a tapped cure. And what it does is it does initially prevent the components from moving. It does provide a small degree of cure. And then with a small pause introduced to allow everything to cool down, and the pause could be less than a second, it's very short. Then with a second, third, or fourth step, we increase the amount of energy delivered to the material to be cured to basically solidify it and lock it in place.
All right, wonderful. Thanks, Roy. Unfortunately, that is all the time we have for questions today, but I would like to thank Divi Gupta and Roy Kaiser, as well as our audience, for joining us, and thanks to all of you who submitted questions. We'll supply Roy and Divi with any that we didn't get to so they can follow up later. In just a moment, a survey will pop up. Please tell us what you thought of today's program by answering 3 quick questions. This webinar will be available on demand for the next year, and an email will be sent to everyone who registered as soon as the archive is ready. Once again, thanks to everyone for watching.
Thank you.